So let's take a look at some examples of how we can use our new integral formula to calculate the total work done by a system. And we're going to start off with a physics example here. It's called Hooke's law. Hooke's law says that the force exerted by a spring that's stretched or compressed x units from its natural position, from the equilibrium position, is given by f of x equals negative k times x, where k is a constant that it depends on the flexibility of the spring. So what I want to know is how much work is done by a spring that was compressed to 0.25 meters when it's released and comes back out to a distance of 0.2 meters past its equilibrium point, right? Assuming that the spring constant is 4 newtons per meter. So we've got our formula here, and I'm just going to put Hooke's formula in here. This is going to be negative 4x dx, and we're going from negative 0.25, that's how much it was compressed by, back out to 0.2. This is a pretty straightforward integral. The antiderivative here is negative 2x squared, and we're going to evaluate that from 0.2 to negative 0.25, and it comes out to about 0.045 joules. Okay, straightforward example, right? Let's take a look at another situation. How much work is done by the same spring, right, the same constant here, if it's stretched to 0.25 meters from its equilibrium point? Okay, this probably seems very similar, right? But we're actually going to get an interesting result here. So it's going to be the same integral, the integral of negative 4x dx. We're starting at the equilibrium point, so x is going to be 0 there, and going out to 0.25. Okay, well, again, we know what the antiderivative is, negative 2x squared. If we substitute those numbers in, we get negative 0.125 joules. Okay, so work can be negative then, yeah? So, I mean, that was kind of predictable based on just what we know about integrals. Definite integrals can sometimes be negative. But what does this mean from a physical perspective? Well, I don't want it's a calculus class, not a physics class, so I don't want to get too deep into the physics of this. But the way this works is, if the motion of the spring is going one way and the force is going the other way, that's when you're going to get a negative value for the work. And that is what's happening here, right? The string is being stretched. So if you visualize it being lined up with the motion line here, it's being pulled to the right, but the spring is exerting a force in the other direction because the spring is always trying to go back to equilibrium. So because the two are going in opposites, yeah, okay, the work should come out negative. So this raises kind of another question. Is it possible for the work done to be 0? Well, there's the trivial case where the object doesn't move, right? Even if a force is being exerted, if the force isn't enough to move the object, then the work done is 0. So, okay, we've got that trivial case. So let's rephrase the question a little bit. Is it possible to have a situation where an object actually moves because of a force and the work still ends up being 0? Well, it turns out the answer to that is yes. Take a look at this case. Suppose we have this same spring, and it's stretched to 0.25 meters from the equilibrium point, and then released so that it goes back to that point. Okay, now how much work is done? Well, if we apply our formula, the starting point is 0, and the ending point is 0. Right? We really don't care what the antiderivative is at this point. In one of the integral rules you learned back in first semester calculus says the integral from a to a of an integrable function is 0. So yeah, okay, the math gives us the answer we were looking for. But can we come up with a physical interpretation of this? How does our physics concept of work justify this answer? Well, remember, we can rewrite the integral, splitting it up into two parts. There's the integral from 0 to 0.25, that's the stretching part. And there's then the integral from 0.25 back to 0, that's the compressing part, where it's going back to the equilibrium position. And these integrals, the only difference is that the bounds are switched, right? So again, kind of going back to our integral properties, the magnitude of these integrals are the same, but they're going to have different signs. So yeah, they're going to cancel out, and the total work is going to end up being 0. So yeah, that is something that could potentially happen. Okay, so let's look at one more example. This time, something that doesn't involve springs. So suppose we have a force of 40 newtons applied to a cart at an angle of 30 degrees. Think it's like a wagon, right? You've got the handle of the wagon and it comes up at an angle. You pull on it and the wagon moves forward. Or we're going to assume that this goes horizontally through a distance of 4 meters. Okay, so what makes this situation interesting is that the force isn't acting in the direction of the motion. Only that portion of the force that's moving the cart along the ground is considered to be doing work. So to answer this question, we have to find the magnitude of that force, right? And we can do that by constructing a right triangle and decomposing it into its vertical and horizontal components. The horizontal component here is the part that's acting in the direction of the motion. We apply just a little, right triangle trigonometry. That piece has a magnitude of 40 cosine of 30, which is 20 times the square root of 3. That's the force that will substitute into the work formula. Now, if we work through this integral, now notice that this is actually the constant force case, right? But if we work through this integral, right, we get 20 square roots of 3 times x, evaluated from 0 to 4. That comes out to 80 square root of 3 joules, or approximately 138.6 joules. And so this is how you would handle a case where the force is not acting in the direction of the final motion. Okay, so now that we've got a number of work examples. We've seen some of the interesting situations that can come up with work in terms of the sign and so forth. In the next lecture, we're going to take a look at another kind of physical example where we think about how we can calculate the force exerted by a body of water on an object that's in the water.